In this video, we'll introduce partial derivatives, which are natural generalizations of derivatives from single variable calculus. So imagine having a function of several variables, let's say a function of two variables, and then there will be a partial derivative for each of the variables. So the partial derivative with respect to x is often denoted by this notation, is by this symbol. This symbol is pronounced del, so it's del over del x of f. Perhaps other notations can be used as f sub x and similar notations. They all refer to the same thing, which is just forming the differential quotient in x, meaning that you take f of x plus delta x y minus f of xy. So this is a small nudge in the x argument, in the first argument, divided by delta x, and delta x is taken to 0, and this limit is the partial derivative with respect to x. Similarly, the partial derivative with respect to y is a similar limit, but there it's the y component or argument that we are nudging. So this limit is the definition of the y partial derivative. So the idea is really, when you do calculations, all you have to do is differentiate the function. Let's say if you want to calculate the partial derivative with respect to x, you differentiate the function f of xy with respect to x as if x is your variable and y you treat it as a constant. Okay, and similarly, when you compute the partial derivative with respect to y, you treat y as your variable, differentiate with respect to that variable, and treat x as if it was a constant. Okay, so let me just give you two quick questions. So one, take the function x cubed times sine of y plus root x and differentiate this function with respect to y. Okay, pause the video and input your answer below. Okay, I hope you paused it and realized when you differentiate this function with respect to y, this second term only depends on x, so it's like adding a constant or the square root of a constant that differentiates to 0, and it's only this term that we care about, or this factor sine of y, which depends on y, and the derivative of the sine function is the cosine function. Here we have this constant multiple of x cubed from the point of view of y, so that remains. So x cubed times the cosine of y plus 0, because that other term does not depend on y, it's like a constant. Okay, so that's the answer. Now my second question is similar, but with a different function. I'm asking for the x derivative of the following function, y cubed times the natural log of root x times y. Okay, so pause the video, compute this x derivative, and input your answer below. Okay, I hope you paused it and realized that it's now being done with respect to x, and there is our x. So when we differentiate this function with respect to x, y cubed is like a constant multiple that remains, and then this is a composite function. So what we want to have is the derivative of log, that's 1 over the argument, so this is it, times the derivative of the inner function, so that's root x times y. So of course that square root of y is just constant multiple, so it's the square root of x that we want to differentiate, and if you remember, that's 1 over root x. So what we really get here is we can, well, of course, simplify by root y. Okay, and what we get is 1 over 2x. Okay, or perhaps, to be precise, the absolute value of x. Okay, so that's the second question. And just to explain what these partial derivatives are, I mean, they can be given a geometric meaning or an interpretation, which is just like with the single variable derivative. There it gave you the slope of the tangent line drawn to the graph of the function. The partial derivatives, we also give you slopes of lines, of tangent lines, which are drawn in either in the x or the y direction. So let me just show you, well, first explain what I mean. So d over dx of f is the slope of the line drawn to the x direction, meaning that the y value is being kept constant, and we only vary the x variable. Okay, and similarly, let me just write that the y derivative is the same thing, the slope of the line drawn in the y direction. Okay, and let me show you what I mean by giving you the following question. Okay, so let's consider the function f of xy equals 4 minus x squared minus 2y squared, and I ask you to compute the partial derivatives with respect to x and y at this point, so 1, 1. So let me use this other notation, the partial derivative with respect to x at 1 and the partial derivative with respect to y at 1, 1. Okay, pause the video, compute these partial derivatives below. Okay, I hope you paused it and put your answers below. So when you differentiate this function with respect to x, you get, well, this is the only term that depends on x, is the minus x squared. So that gets differentiated to minus 2x, and that you have to consider at 1, 1, which gives you minus 2. Okay, x equals 1 gives you minus 2, and similarly with respect to y, we only care about this term. When we differentiate, all the other terms differentiate to 0, and that term differentiates to minus 4y, which when we substitute x equals 1, y equals 1, we get minus 4. Okay, so minus 2 and minus 4 are the two numbers that we get. So these are the two slopes that we'll obtain if we take the graph of this function. So this is what we see here is the graph of 4 minus x squared minus 2 y squared. And let me just show you if I, so that's a point, something like 1, 1. And let me show you that by computing the x derivative, we get minus 2. That's the slope of that blue line. So we are cutting through the graph with a plane parallel to the xz plane. So y is kept constant, and we get minus 2 for the slope there. If I compute the y derivative, we are cutting through the graph with the plane parallel to the yz plane. So x is being kept constant, and then the slope we are getting is the slope of that red line, tangent line that we get there. So I hope you enjoyed this video, and I'll see you in the next one.